Hey folks, let's talk measured numbers and how we handle them, and density and significant figures. I know that sounds like bad news to you guys, but I'm going to make it tolerable, try to make you understand why we just can't write as many numbers as we want when there's a calculated result. So let's talk density and sig figs right now. Konnichiwa, everyone. Konnichiwa. Mike here. Today we're going to talk about measured numbers and significant figures. So hey, check me out. I'm doing art for you guys. That's a little cartoon of a graduated cylinder. And notice I made a little curvature because that's what water does when you put it into a tube like that. It will, the surface tension of water will make a meniscus. And what we usually do with these things is they're calibrated to take into account the meniscus, and we read them from the bottom. Now, notice that that number is 10 milliliters. That number is 20. So if we do what we call in science count lines, you could see that there's 10 lines in between 10 and 20. And so this particular thing, by the way, just for the buzzword of it, is called the increment. All right, and in this case, the increment is worth a milliliter. Now, not always, but most of the time you strive to do this measurement with a sort of an honest portrayal of how many numbers there are, and we call those numbers significant figures. So let me try to explain. Go ahead and in your mind, now don't be afraid to get it wrong, all right? I want you to tell me what that number is for that measurement. Go ahead, you might have to, pause your video or whatnot, but I'm gonna go ahead and do that measurement. And so 11, 12, 13, 14, 15, 16. Now, let me explain. 16. And now you could say it looks like it's about halfway up, and a little bit more actually. So here's what you don't do. You're not going to say, well, I'm going to round it up to 17 milliliters. You don't do that. We don't round until after a calculation usually. But what I can do here is I can say, I think given the spacing of those lines, I have the human ability to be able to get one more digit out of that. And so I'm going to call that 6/10 of the way up, and I'm going to call that 16.6 milliliters. So let's go over here in the naughty corner. Wrong thing. Put a little frowny face there. It's a shameful little, with a dunce cap. Now, what you don't want to do is say, well, 16.60, because I just wanted to throw a zero on there. You can't say that. I can't say that I've measured that 60/100ths of the way between the lines. I'm not capable of that. I'm not going to round it. Sometimes I'll see my students and something will land on 0. For example, if that was right on that line, you wouldn't call that 17 or 16, you'd call it 17.0. So since you have the ability to be able to measure to 3 digits, you do that even when it's on the line. So that number not only says what the volume measurement's going to be, but it also says that I can accurately to 3 digits determine that volume. So, and let's go ahead and let's say we did this, we converted it to liters. That would be 0.0. There's 1,000 milliliters in a liter, so this would be 0.0166. Oops, not milliliters, liters. Do you notice how the number of digits change their total, but the zeros are not what we call significant? We're going to talk about that in just a little bit. So the fact is, if I converted that to the other units, it doesn't really change the fact that that measurement was good to a 1/10 of a milliliter, which is 0.0001 1 liters, right? Our accuracy didn't change just because I changed the units. Just to prove to you, if I converted that to scientific notation, that would be 1.66 times 10 to the 2, but it's smaller than 1, so minus 1. And so you'd have 3 digits there, you'd have 3 digits there, and then we call these zeros not significant. All right, so, and there's just some really basic rules about these things, and so that's what we're going to talk about next. But do you see where those zeros are just there on the second version of my measurement in liters? When something's just a small number, you're just going to tack zeros on it, and you don't want to throw zeros on either end, you know, unless you have to. So, for example, when I converted that to liters, it had to have 2 zeros there, but I wouldn't want to just go throw more zeros on here. 16 point, I'll be ridiculous. Maybe you just like zeros. Well, you're kind of fibbing there, folks. If you just go ahead and throw 3 more zeros on there, that's trying to say that I measured that to a 10,000th of a milliliter, which you didn't. So you see, a lot of this is basically just good judgment. Now, let's talk about all the different forms numbers can take on. And if you have a number that is measured, how do we count the number of measured digits when we just are looking at a number? That's next. All right, folks, let's talk about rules for handling measured numbers, and we've already kind of called these significant figures here. I've thrown that term around, I think, at least once. So basically, significant figures just means how many measured numbers. And I think I proved to you that zeros are sometimes kind of cheeky if they're on either end of the number. For example, that measurement we did with volume, you notice when I converted it to, I had to convert it to liters, and I had to throw in 2 extra zeros, and those weren't really measured zeros. They're just there because the number is big or small. So what happens is you have 2 kinds of zeros. You have the ones to the left, and if you had one sandwiched in the middle, that would actually be a real thing. But if this right here, what's bothering me, that doesn't have units on it. I keep saying everything. Let's just call that grams. Now, folks, one way to really easily discern how many significant figures you have is we could convert it to scientific notation, right? 1, 2, 3, 4, 5, 6. We'd say 1.2 times 10 to the minus 6 grams. Now, that makes it really easy because the number that is the partial power of 10 in scientific notation, the number of digits you have there, that's simply how many significant figures there are. Or you just don't count the zeros. Either way, we would say this has 2 significant figures. And that would be our answer. Now, I'll show you why we care later. Let's say this is 155,000 grams. When you have a 0 to the right, same sort of deal. And then what we would do is say, well, someone wrote that number, and they really know that that number is good to between 156,000 and 154,000. So you really only have 3 significant figures here, and so that's a trailing 0. Now the other, so we would say that has 3 sig figs. Sig figs is the cool way to abbreviate it. Saves you 13 seconds every semester. And now the only exception is once in a while, if you see something like they put a decimal point there, then that's a different ball game. If that, you count them all. That decimal point means, yes, I measured that to a single gram, and it just happened to be by dumb luck fell right on a bunch of zeros. Then you would say that has 6 sig figs. But you know what? Good thing, folks, we're not going to give you 155,000 grams of stuff. The other thing I could do is I could convert that to kilograms, right? And that would be 155 kilograms. And I'd write it with 3 digits, unless that decimal point was there. And luckily, we don't see numbers of that nature in this course. We're going to see crazy big or crazy high numbers usually. Now, what happens, folks, next is kind of important. If you do a calculation on a number, you're going to either do addition or subtraction, or you're going to do multiplication and division. And what happens is you're going to limit how many significant figures you have based on the weakest or least accurate measurement. So you've always heard of like what would happen, you know, like a team is only as good as its worst player, you know. So if you went and made me the kicker for the, I had to be kicker, folks, in case you haven't seen me, I'm not a huge guy. But if you made me the kicker for the Bengals would become, I know I almost want to say better, but that's not a funny joke. The Bengals would become a lot worse because I could only make maybe a 30-yarder or so, because I used to be a kicker in high school. So, but nonetheless, you have to kind of pay attention to what sort of mathematical operation you're doing. Now, good thing is adding or subtracting, you're going to be using the same kind of units, you know, milliliters. And then what you do is you pay attention to decimal places. So for example, what if that was measured on our little graduated cylinder I made a cartoon of? And you would, you know, and then you plunk a piece of metal in there and you try to do liquid water displacement. You can see that that would be, that number minus that number would be 7.5. So I happen to have less total digits just because it happened to go below 10, but I don't have to worry about that. It was the same gizmo that I'd use to measure it. And when you add or subtract, it's usually like, oh, I just took two things on a balance and I added them together in grams, and they're both good to 1/1000th of a gram. Or in this case, these are both good to 1/10 of a milliliter. So that's what you do when you're adding or subtracting. Different ball game when you are multiplying or dividing. Most of the time we'll be dividing. So for example, the next thing we're going to do is a density experiment. And you're going to do it along with me. And let's say, what if that was like, well, it's not very realistic, but some crazy accurate balance. In our labs, back when we had labs, this would be good to 1/10,000th. Our good balances are good to 1/10,000th of a gram. So let me get rid of that. That's silly. You know, we don't have balances that go to, you know, millionth of a gram. And then, you know, you would take and divide that by milliliters. Notice the units are different sometimes when you do this. And I was just being lazy because I just wanted to divide by 1, so I made 1 in there. So what you've got is you've got here, this has 6 sig figs. This has 2 sig figs. And so the fact that we had to measure the volume and didn't get as much accuracy out of it, whatever your result, it's better have 2 sig figs. So you go with the lowest number of total sig figs. So 6 divided by 2 sig figs, your answer better be expressed in 2 sig figs. So for example, when I do this calculation, I get 70.1792, and this is where you round. You don't round until the end. So what you would do is you would then say this is 70. I don't know what the heck kind of density this thing is. Nothing has a density of 70, but I was just making stuff up. So you would have to report that in 2 significant figures, because the volume measurement being less accurate spoils the whole calculation, because the calculation on 2 measured numbers is going to be subject to the weakest number. Now, one thing I forgot to mention here, and I better write this down. What if you had to do something like this? 1.579. Okay, let's make that something like, let's make that inches. And we're going to convert it to centimeters. 2.54 inches, dang. 1 inch is 2.54 centimeters. Now, this is a constant. That's not measured. So what you do with this is you consider that to be, that's the truth. 12 inches is a foot, that's the truth. The speed of light is 3.0 times 10 to the 8th meters per second, that's the truth. And so what you would do is you'd say this has, well, in this case that had 4 sig figs. This has infinity sig figs. And then I'll just crunch out a number on my TI-30 $10 calculator times 2.54, and I hope we come up with something weird. 4.0 0.01066 centimeters. Now what I would have to do is take the lower number. I'd have to round that to 4 digits. And so I would, and now don't just chop them off. You know, there's 4 digits right there. But what I'd have to do is I'd have to factor in what comes after it, and because that's above, you know, it's more than halfway between 0 and 1, I would have to call this 4.011. See, so I had to round it up. I don't just chop off and truncate those. Whoopsie. That's what we call in science bad camera work, but I was kind of winging it there. So you see, with constants, they shouldn't limit anything. They're not measured. So when you're doing a calculation on 2 measured numbers, you treat it differently than a measured number that's being multiplied or divided by a constant. All right? Let's put this stuff into action with my little iron cube sample. We're going to do the density of this thing next. Hey folks, check out my cube. Isn't it cute? I'm real proud of it. It's mine. I used to have it in my office back when I went to my office. Now it's here on my kitchen table. You notice it says 10 ounces, but we're not going to take that for literal. We're gonna actually determine it because, hey, you know how things are. Times are tough, folks. I'd like to use our crazy, great, accurate, good to a 10,000th of a gram balance that we have in the lab, but we don't have that. So what we're going to do is we're going to do the density of this cube. I know what the literature value of iron should be. It's actually on that cube. And so we're going to, I know Mike just talked about not having formulas and don't memorizing formulas, but we're going to go ahead and calculate the density of this thing. So on to our balance goes, I don't know how good you can see. There goes our, okay, that says 288 grams. Now I'm feeling pretty good about that because what's going on now is that's about 10 ounces. So let's write that down. Okay, 288 grams. And then here, folks, this is what we call, oh, stop it. I'm going to take that off there. There we go. And just let that chill out over there. This is what we call in science a ruler. All right? And then what I'm going to do, to the best of my ability, is I'm not going to do it in cubic inches. I'm going to do it in, I'm going to find the volume. Now, if you don't know how to do the volume of a cube, it's real simple. L times itself 3 times. And so what I'm going to do, let's get my glasses on, and to the best of my ability, which might not be good, I'm gonna go, oh, you know what, this is a nice ruler too, because it's got the line not on the end where they get rounded off. Okay, this is bringing up an excellent point. It's a good thing that that's right on the line, because these lines are so darn close that I don't think I could even stand a chance to read 1/10 of the way through those. So you know what I'm going to do, folks? I'm going to say that was 3.3, by the way. 3.3. And why did I not call it 3.30? Because, folks, I can't see. Those lines are so close together that I can't read how many tenths there are. So I'm gonna limit myself to 2 sig figs. And so see that whole thing, you want to go 1 past the increment. The increment was a millimeter, but I can't determine the to 1/10 of a milliliter. That's super. That's like 100 micrometers. So okay, 3.3 cubed, 35.937. Now, remember this. Let me write that in there. 35.937 centimeters cubed, which is the same thing as a milliliter. Okay, now folks, some of you might be getting irritated right now. You say, hey, you didn't chop that down to 2 digits. And you know why I didn't do that? Because you only want to round at the end. So what I have to do is recognize that that had 3 sig figs. And then that had two sig figs. So even though when I cubed it, it got to be a bigger number, I'm going to call that 2 sig figs. And if I truncated it now to call it 36, I'd lose some accuracy. So you really only want it round at the end. So 288 divided by 35.937. 8.014. I'm going to do this to be ridiculous, okay? I'll show you how ridiculous look, calculators don't know sig figs. They don't know the etiquette of sig figs. They just give you a number, and if it doesn't land on some weird 4.3 grams per, I'm going to call it a milliliter, same thing. Now I'll see people do some things like that's their answer. And I'll be like, really? You know that? To a almost a millionth of a gram per milliliter? You don't. You know that to 2 digits, folks. 2 digits is all you know that to, because the volume, because of my bad eyes, or actually I don't think I have that bad eyes. I have my glasses on, but it's just that ruler, it's hard to measure to unless I had a magnifying glass, I can't measure it to more than 2 digits. I'm going to call that, I don't have to round this up, I have to round it down, 8.0 grams per milliliter. And that's our answer. And then if you see the cube here, he's got it right on there. What's it say? 7.86. So our error isn't that bad. You know, we came pretty close to the literature value with a postal scale and a ruler. As a matter of fact, I got, 10% error would be if I was off by 0.8. So I was off by way less than that. So pretty good accuracy there. I'm kind of feeling almost pretty good about myself, as much as that would happen. So here's what I'll see students do in lab. You know, they'll be massing this thing, you know, and they'll be on the balance. And let's say it's something that's not 288 grams, it's something more realistic. They'll get like 1.100 grams on a really good balance. And then what I'll see that they do is they don't write it down like that. The balance even says that. They'll be like, oh, that's 1.1 grams. And then I'll say, hey, why'd you throw all those numbers away? And they'll be like, I'm rounding. And I'll be like, stop that. You don't round until you've done your calculation at the end. You don't take perfectly good numbers and throw them away. Like when I did that when I did the other thing earlier, I didn't just take and truncate numbers. So you only round at the end. And that's the gist of sig figs. I think you've had a good experience with about everything that you would run into in the world of the etiquette, really. It's kind of the etiquette of scientific measured numbers. You don't want to understate it or overstate it. Your number not only is a number, it's got a unit with it, but it also, by the number of digits, tells the reader how accurate that measurement was. So, very good, folks. Have a good rest of your day, and we will see you next time. Farewell.